look at properties of elements. Three in particular: atomic radius, ionization energy, and electronegativity. Let's start off with atomic radius. Atomic radius is just as it sounds, it's the size of the atom. We are able to measure that size of the atom by taking two identical atoms. For instance, let's say these two atoms here are hydrogen. And we know that hydrogen has one positive proton in its nucleus. So scientists have been able to link two identical atoms together and measure the distance between the nucleus of them. They take that distance between them and divide it by 2. And that gives you what we call the atomic radius. So the atomic radius is determined by taking the distance between two nucleus of identical atoms and divided by 2. We usually, the units they usually measure these in are picometers, and that would be the primary unit we would refer to, or angstroms. Um, it's hardly used, but is able to be measured in angstroms. So next, we're going to look at the pattern, the trend of the atomic radius. So if we look here on the periodic table, look at lithium. The size of lithium radius is 152 picometers. But as you go across the periodic table, you see lithium now, next to lithium is beryllium. Its size is 111 picometers. And then if you continue across to boron, its size is 82 picometers. Notice the pattern? Here, the atomic radius tend to decrease as you go across any period because the atomic number increases. So what that means is if you have an element like lithium and it has its 3 protons and it's in the second period, that means it only has 2 energy levels. But barium right next to it has 4 protons and it still has 2 energy levels, but because of the increase of the protons in the nucleus, it is contracting, pulling in on those valence electrons, causing the atom as you go across the periodic table decides to get even smaller because you're increasing the protons. And those protons in that center is really pulling in, because you know opposites attract, pulling in on the valence electron, causing the atom's size to decrease as you go across the period. But it's just the opposite as you go down a group. So as you go down a group, the atomic radius tends to increase. The size of the atom gets bigger as you go down a group. That's because they're gaining more. So, looking at the atomic radius as it goes down a group, it increases because of the atomic number increases the number of protons and electrons. So, for instance, if you look at lithium, it has 152 picometers, but sodium right underneath it in the third period has 186, and then potassium is 127. Therefore, the size of an atom is increasing as you go down a group. And the reason why it's increasing going down a group is because of the number of energy levels are increasing. So lithium has, it's in second period, has 2 energy level, whereas sodium is in the third period, it has 3 energy levels. They're increasing the number of protons and the number of electrons. So those electrons have to go to the next energy level once the previous one is filled. So again, the atomic radius the atomic radius increase as you go down a group, and atomic radius decrease as you go across a period. So keep those trends in mind. Next up, we have something called ionization energy. But before we get into ionization energy, we need to know what ions are. We have to define ions. Ions are charged atoms made by losing electrons, and when they lose electrons, they form cations, a positive charge, or when they gain electrons. When they gain electrons, they gain a negative charge called anions. But we're going to focus on ionization energy, which is the energy required to remove electron, one or two valence electron to form a cation. So energy in, the energy that goes in is called ionization energy. And if you give it enough energy in, electron comes out. So let's take a look at that. This usually occurs with metal elements the most. So ionization energy is measured in the units of kilojoules per mole. So lithium, for instance, I'm just keep picking on lithium, has an ionization energy of 520 kilojoules. And that's because lithium valence electron is in the second energy level. So it would take 520 kilojoules to knock that one valence electron out. Same for sodium and potassium. Potassium is in the fourth period, so it has four energy levels. And on that fourth energy level, it would only take 419 kilojoules to knock that valence electron off. And that's because the valence electron is further away from the nucleus. So the nucleus of potassium is 19 protons. But that valence electron is four energy levels away. So the 19 positive protons cannot hold tight to that one valence electron that's far away. And the reason why it cannot hold tight to that one valence electron far away is because of something called the shielding effect. Shielding effect are all the inner electrons that blocks the whole of the protons in the nucleus on that one valence electron that's far away. So there are two reasons. Valence electron is further away from the nucleus, and there's something called the shielding effect caused by the inner electrons. They block the hold that the nucleus have on the valence electron. So as you go down a group, ionization energy will decrease. So I'm gonna write that down. Down, down group, ionization energy decreases. All right. However, it's not the same as you go across a period. Notice again, lithium is 520, but beryllium, which is right next to it, is 888. 899 kilojoules. And that's because the size, there's four protons and just two energy level with those two valence electrons. To lose just one of them, 899 kilojoules have to be supplied to this atom, and one of those valence electron would get lost. But because the atom is smaller and there's less of shielding effect, it's less shielding effect. So that means the nucleus have a stronger hold over the valence electron. So the trend of ionization energy as you go across a period generally increases. But if you notice here, the general trend takes a little dip. So we have 520 for lithium, 899 for beryllium. Boron goes to 801, and then carbon goes up, nitrogen goes up, and oxygen goes up. The reason why there's a little dip in ionization energy is because these are the elements that introduce the p orbitals. Okay? So the general trend of ionization energy, down a group it decreases, but across a period it increases. I hope you guys could see this. So, the next thing we're going to talk about is electronegativity. Electronegativity is the tendency of an atom to attract shared pair electrons towards itself. So notice this atom here in red is really pulling on this electron from this other atom. It really, 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 really wants it. It has a tendency to want electrons. And let's look at the chart here. Nonmetals tend to have a high electronegativity. Electronegativity, I'm going to symbolize with the letter En. It's on a scale, a short scale of 0 to 4. 4 being the highest. And the only element that has 4 for electronegativity is fluorine. And that's because fluorine has 7 valence electrons that are close to its nucleus, which has 7 positive. So this 9 positive nucleus, the non-positive protons in the nucleus has an attraction to gain another electron. It's pulling on some electron from outer space, I guess you could say, to make a valence electron on this last energy level to have the octet rule. Therefore, all nonmetals, not all nonmetals, but most nonmetals have high electronegativity. But metal elements have low electronegativity because metals do not desire to have electrons. They want to get rid of their electrons, not take on any new ones. So the trend for electronegativity as you move across a period, it increases. But as you move down a group, it decreases. Ah. So as it moves down a group, it decreases. And that is electronegativity. So those three, atomic radius, ionization energy, and electronegativity, all relates to chemical reactivity. And chemical reactivity is the ability of a substance to interact chemically to another substance to form a new substance, a new compound. Therefore, the reactivity for metals increases in this direction because the smaller the atom, the easier it is to lose electrons, valence electrons, because metals want to lose valence electron. So it's easier to lose them on this side because they have less to lose. And reactivity increases going down a group on the metal side because the valence electrons are further away. So that makes them extra easier to be lost. Now, it's the total opposite for nonmetals. Nonmetals reactivity increases as it goes up because the atoms are smaller. So they draw in valence electron, and they increases as you go across the period from left to right because they have more electrons to, I mean, more protons to pull in valence electron. So that is the periodic table, some of the properties of certain groups, and the trends of the three major properties: atomic radius, ionization energy, and electronegativity. This is the summarization of it all. Thank you.